The first stage of the Apollo 11 Saturn V, designated S1C6 for the sixth flight stage, arrived at the Kennedy Space Center on February 20th, 1969. Because of their large size, Saturn V stages were shipped to the Kennedy Space Center by ocean-going vessels and specially designed aircraft. The Saturn V was the first large vehicle in the U.S. space program to be conceived and designed for a specific purpose, that of landing a man on the moon and returning him safely to Earth. The birth of the Saturn V can be dated to January 10, 1962, when NASA formally announced development of the Big Booster. The 300,000-pound first stage is 33 feet in diameter and 138 feet long. At liftoff, it held nearly 4.5 million pounds of propellant, consisting of RP-1, a form of kerosene for fuel, and liquid oxygen as oxidizer. The first stage generated a total thrust of around 7.5 million pounds, operating for just 2.5 minutes to lift the vehicle to an altitude of about 38 miles at burnout. The awesome power of the Saturn V first stage was generated by 5 F1 engines. Each F1 engine was a single-start, 1.5 million pound fixed thrust engine. All of the engines were identical with one exception. The outer 4 swiveled or gimbaled for steering control. The center engine was fixed. The expense of the Saturn V makes it imperative that no effort be spared to assure that it will perform as expected in flight. The magnitude of the Saturn V ground test program was unprecedented. To qualify for flight, all components and systems had to meet standards deliberately set much higher than actually required. The inspection to which flight hardware was subjected was thorough. X-rays were used to inspect fusion welds, 100 castings and 5,000 transistors and diodes. A 1/4 mile of welding and 5 miles of tubing were inspected with the use of ultrasonics. The same type of inspection was given to adhesive bonds, which are equivalent in area to an acre. An electrical current inspection method was used on 6 miles of tubing, and dye-penetrant tests were run on 2.5 miles of welding. Each contractor had its own test program that was patterned to a basic conservative approach. Qualification testing of parts, subassemblies, and assemblies was performed to assure that they are capable of meeting flight requirements. Reliability analysis was conducted to determine the range of failures or margins of error in each component. A battleship test stage constructed more solidly than a flight stage was used to prove major design parameters. The stage verified propellant loading, tank and feed operation, and engine firing techniques. Battleship testing was followed by all systems testing. Finished work undergoes functional checkout to ensure it meets requirements. Fluid-carrying components are subjected to pressures beyond normal operating requirements. Rocket engines were static-fired before delivery to the stage contractor, and each stage underwent testing leading to a full-power captive acceptance firing. After refurbishment and a post-firing checkout, it was shipped to Kennedy Space Center. Upon arriving and being offloaded at the dock, the stage would enter a low bay of the VAB, or Vehicle Assembly Building. The VAB consists of a high bay area 525 feet tall, a low bay area 210 feet tall, and a 4-story launch control center connected to the high bay by an enclosed bridge. There are 4 assembly and checkout bays in the high bay area. The low bay contained 8 stage preparation and checkout cells equipped with systems that simulated stage interfaces. Saturn V stages went into the VAB low bay area where preparation and checkout began. After being towed into the high bay area and positioned under the 250-ton overhead crane, slings were attached to the first stage and attached to the crane. The stage is lifted to a vertical orientation and then positioned over the mobile launcher. At this stage in the process, the first stage is still missing the engine nozzle extensions and fairings and fins. These will be added later. The VAB had 141 different lifting devices at the time of the Saturn V, ranging from 1-ton mechanical hoists to two 250-ton high bay bridge cranes. Each pair of high bays shares a bridge crane. The cranes have a lifting range of 456 feet and a travel distance of 431 feet. When the stage is positioned over the mobile launcher, it is lowered into place. Then it is secured to 4 hold-down and support arms. These support the entire space vehicle during launch preparation and provide hold-down during thrust buildup prior to launch. The second stage for the Apollo 11 Saturn V S-26 arrived at Kennedy Space Center on February 9, 1969. On the Saturn V, the second stage employed cryogenic propellants of liquid hydrogen and liquid oxygen. For the lunar mission, the second stage takes over from the first stage at an altitude of about 38 miles and boosts its payload of the Saturn V third stage and the Apollo spacecraft to approximately 114 miles. When its 5 J2 engines ignite, the stage is pushing more than 1 million pounds. Speed of the stage ranges from 6,000 miles per hour to 15,300 miles per hour. The beginning of the second stage boost is a two-step process. When all the F1 engines of the first stage have cut off, the first stage separates. Ullage rocket motors around the base of the second stage then fire for approximately 4 seconds to give positive acceleration to the stage prior to engine ignition. About 30 seconds after the first stage separation, the part of the second stage structure on which the Ullage rockets are located, the aft interstage, is separated by firing explosive charges. This second separation is a precise maneuver. The 18-foot high interstage must slip past the engines without touching them. With the stages traveling at great speed, the interstage must clear the engines by only a little more than 3 feet. The second stage burns for about 6 minutes, pushing its payload into space. The 81-foot second stage is basically a container for its 942,000 pounds of propellant, with engines attached at the bottom. Propellants represent more than 90% of the stage's flight weight. The stage is constructed mostly of lightweight aluminum alloys ribbed in such a fashion that it is rigid enough to endure the pressures to which it is subjected. Special lightweight insulation had to be developed to keep its cryogenic propellants from warming. The second stage developed its power through 5 Rocketdyne J2 engines, a high-performance upper-stage propulsion system. Each engine developed a maximum vacuum thrust of 225,000 pounds. All J2 engines were identical when delivered. They all were designed to be restarted in flight. The restart capability is only used in the third stage. As in the first stage, the outer 4 engines in the second stage gimbal, while the center engine is fixed. The second stage of the Apollo 11 Saturn V was erected at the top of the first stage on March 4, 1969. Using the 250-ton bridge crane, the stage was lifted into position with the aft interstage attached. The Apollo 11 Saturn V's third stage was moved into the VAB for checkout on January 21, 1969. The Saturn V third stage was an oxygen-hydrogen stage derived from the S4 stage originally created as part of the Saturn I program. The S4B stage was also used as the second stage for the Saturn 1B. The third stage had a maximum thrust on one J2 engine of 225,000 pounds. The stage was used for the final Earth orbital insertion and reignited to place the Apollo spacecraft on a trans-lunar trajectory. The stage burned for about 2 3/4 minutes for orbital insertion and about 5.5 minutes for trans-lunar injection.
Ignition.
We confirm ignition and the thrust is go.
Guidance looking good. Velocity 26,000 feet per second. Cut off. We're showing velocity 35,570 feet per second, altitude 177 nautical miles.
Apollo 11, this is Houston. We show cutoff and we copy the numbers and now 62. Apollo 11, Houston, do you read? Apollo 11, this is Houston. Do you read, over?
Roger, Houston, Apollo 11. We're reading a VI of 35579er, and the EMS was plus 3.3, over.
Roger, plus 3.3 on the EMS.
Because the stage was a part of the vehicle for an extended period of time, it contained an auxiliary propulsion module for attitude control. 2 APS modules were mounted 180 degrees apart on the aft skirt assembly. Each module contained 3 150-pound thrust engines and 1 70-pound thrust ullage motor. The Apollo 11 third stage, with its aft interstage, was placed above Stage 2 on March 5, 1969. The instrument unit is the Saturn V's nerve center. It contains the electronic and electrical equipment needed for guidance, tracking, and communications of vehicle environmental and performance data. The IU also contains environmental control equipment for temperature control, batteries, and power supplies to furnish operating power for electronic equipment. The stage structure is 260 inches in diameter and 36 inches high and becomes a load-bearing part of the vehicle. It supports the components within the IU and the weight of the spacecraft. Several tracking systems are used to follow vehicle trajectory during ascent and orbit. Vehicle antennas and transponders, which increase ground-based tracking systems' range and accuracy, make up the IU's tracking equipment. The Saturn V is equipped with lots of equipment designed to detect malfunctions, Some of this equipment checks engine thrust and monitors guidance computer status, attitude rates, angle of attack, and abort request. This emergency detection information is flashed to the IU where it is routed to the emergency detection distributor in the electrical system. In the case of an emergency, the system will turn on a light in front of the astronauts. If the spacecraft abort selector switch is in the automatic abort position, the abort will take place without further crew participation. The action cannot be vetoed by the astronauts. However, if the selector switch is in the manual position, the crew makes the decision when to abort a mission. The Apollo 11 lunar module, LM-5, was designated as Eagle by the crew. The lunar module is a two-stage vehicle designed for space operations near and on the Moon. The LM is not capable of re-entering the atmosphere and was the first manned spacecraft designed solely for operation in space. The lunar module stands 22 feet 11 inches high and is 31 feet wide diagonally across the landing gear. Joined by 4 explosive bolts and umbilicals, the ascent and descent stages of the LEM operate as a unit until staging, when the ascent stage functions as a single spacecraft for rendezvous and docking with a CSM. 3 main sections make up the ascent stage: the crew compartment, midsection, and the aft equipment bay. Only the crew compartment and midsection are pressurized at 4.8 pounds per square inch. The cabin volume is 235 cubic feet. The descent stage consists of a cruciform load-carrying structure of 2 pairs of parallel beams, upper and lower decks, and enclosure bulkheads. The center compartment houses the descent engine, and descent propellant tanks are housed in the 4 square bays around the engine. The descent stage measures 10 feet 7 inches high by 14 feet 1 inch in diameter. In a retracted position until after the crew mans the LEM, the landing gear struts are explosively extended and provide lunar surface landing impact absorption. The main struts are filled with crushable aluminum honeycomb for absorbing compression loads. Foot pads 37 inches in diameter at the end of the landing gear provide support on the surface. Each pad except the forward pad is fitted with a lunar surface sensing probe which signals the crew to shut down the descent engine upon contact with the lunar surface. Eagle had a launch weight of 33,205 pounds. CSM-107, Apollo 11's Command and Service Module spacecraft, was designated as Columbia by the crew. It consisted of a service module 12 feet 10 inches in diameter and 24 feet 7 inches high. For the Apollo 11 mission, it weighed 51,243 pounds at launch. Aluminum honeycomb panels 1 inch thick form the outer skin, and milled aluminum radial beams separate the interior into 6 sections around a central cylinder containing 2 helium spheres, 4 sections containing service propulsion system fuel and oxidizer tankage, another containing fuel cells, cryogenic oxygen and hydrogen, and 1 section essentially empty. The service propulsion system provided thrust for large spacecraft velocity changes through a gimbal-mounted 20,500-pound thrust hypergolic engine using a nitrogen tetroxide oxidizer and a 50-50 mixture of unsymmetrical dimethylhydrazine and hydrazine fuel. The command module is a pressure vessel encased in heat shields, cone-shaped 11 feet 5 inches high with a base diameter of 12 feet 10 inches and a launch weight of 12,250 pounds. The command module consists of the forward compartment, which contains 2 reaction control engines and components of the Earth landing system, the crew compartment or inner pressure vessel containing crew accommodations, controls and displays, and many of the spacecraft systems, and the aft compartment housing 10 reaction control engines, propellant tankage, helium tanks, water tanks, and the CSM umbilical connection. The crew compartment contained 210 cubic feet of habitable volume. The command module Earth landing system includes the drogue and main parachute system, as well as post-landing recovery aids. In a normal entry descent, the command module forward heat shield is jettisoned at 24,000 feet, permitting mortar deployment of 2 reefed 16.5-foot diameter drogue parachutes for orienting and decelerating the spacecraft. After drogue release, 3 mortar-deployed pilot chutes pull out the 3 main 83-foot diameter parachutes with 2-stage reefing to provide gradual inflation in 3 steps. 2 main parachutes out of 3 can provide a safe landing.
Apollo 11, Houston, you're a go for TEI, over. Apollo 11, thank you.
This is Apollo Control at 134 hours, 48 minutes. It continues very quiet here in Mission Control. The flight controllers have been observing the crew inputs to their computer, monitoring as the crew prepares for the trans-Earth injection burn, scheduled to occur at about 35 minutes from now. This is Apollo Control. We're now less than 30 seconds from the time at which trans-Earth injection is scheduled, the burn to start Apollo 11 on its trajectory back to Earth. We're now 15 seconds from the scheduled ignition time. That burn will last about 2 minutes 28 seconds and consume 10,000 pounds of propellant. And the crew should be burning at this time. Of course, that maneuver is performed on the backside of the moon. We have no data from the spacecraft here in Mission Control at this time. We won't know how the burn went for about another 10 minutes, which is the time at which we're scheduled to reacquire Apollo 11.
AOS.
And there's the cue. We have acquisition of signal.
Hello, Apollo 11, Houston, how did it go, over? Help to open up the LRL doors, Charlie. Roger, we got you coming home. It's well stocked.
At launch, the lunar module is housed in the spacecraft lunar module adapters section. This is a truncated cone 28 feet long extending from the top of the instrument unit to the bottom of the service module. The entire assembly of CSM, LEM, and spacecraft lunar module adapter are assembled, moved to the VAB, and erected atop the 3rd stage of the launch vehicle.
There she goes. It was a good one. Roger, Dodger. We got Eagle looking good. It's holding cabin pressure, and it picked up about 2 feet per second from that jettison. I believe that. I can see some cracks in outer coating around the tunnel. In the thermal protective covering. I don't think it has anything to do with pressure. Roger. Hello, Columbia, Houston. We'll have a attitude and a little blip burn for you at about 130.30 so we can separate from Eagle, over. That's fine. Columbia. Columbia. Houston, would you start a maneuver to about pitch of 230 for this little tweak burn over?
Roger, pitch 230.
Roger, Mike, can verify track mode in auto for the high gain.
The crewmen of Apollo 11 spent more than 5 hours of formal crew training for each hour of the mission's 8-day duration. This training included detailed briefings on spacecraft systems, operation and modifications, Saturn launch vehicle briefings on countdown, range safety, flight dynamics, failure modes, and abort conditions. Briefings were held and continuous training done on mission photographic objectives and use of camera equipment. Stowage reviews and practice in training sessions in the spacecraft mock-ups and command module simulators allowed the crewmen to evaluate spacecraft stowage of crew-associated equipment. More than 400 hours of training per man in command module and lunar module simulators were conducted, along with entry corridor deceleration profiles at lunar return conditions in the centrifuge. Lunar surface briefings and 1G walkthroughs of lunar surface EVA operations were conducted. In addition, the crew became familiar with the flight hardware through visits to the manufacturing facilities and through altitude chamber runs with both spacecraft. In these runs, the spacecraft were placed in a condition simulating flight pressure. The mobile launcher is a transportable launch base and umbilical tower for the space vehicle. 3 mobile launchers were used at Launch Complex 39. The launcher base is a 2-story steel structure, 25 feet high, 160 feet long, and 135 feet wide. It is positioned on 6 steel pedestals 22 feet high, both in the VAB and at the Launchpad. At the Launchpad, the launcher was also stiffened by 4 extendable columns designed to counter rebound loads if the Saturn engines cut off. The umbilical tower, extending 398 feet above the launch platform, is mounted on one end of the launcher base. A hammerhead crane at the top has a hook height of 376 feet above the deck. The 12 million pound mobile launcher stands 445 feet high when resting on its pedestals. The launch vehicle sits over a 45-foot square opening which allows an outlet for engine exhaust into the launch pad trench containing a flame deflector. This opening is lined with a replaceable steel blast shield, independent of the structure, and is cooled by a water curtain initiated 2 seconds after liftoff. There are 9 hydraulically operated service arms on the umbilical tower. These service arms support lines for the vehicle umbilical systems and provide access for personnel to the stages as well as the astronauts to the spacecraft. On Apollo 11, one of the service arms is retracted early in the count. The Apollo spacecraft access arm is partially retracted at T-minus 43 minutes. A 3rd service arm is released at T-minus 30 seconds and a 4th at about T-minus 16 seconds. The remaining 5 arms are set to swing back at vehicle first motion. The Apollo Access Arm, Service Arm 9, located at the 320-foot level above the launcher base, provides access to the spacecraft cabin for the closeout team and astronaut crews. The flight crew boards the spacecraft starting at about T-minus 2 hours 40 minutes. The Apollo 11 vehicle is secured to the mobile launcher by 4 combination support and hold-down arms mounted on the launcher deck. The hold-down arms are cast in one piece, about 6 by 9 feet at the base and 10 feet tall, weighing more than 20 tons. Damper struts secure the vehicle near the top. After the engines ignite, the arms hold Apollo 11 for about 6 seconds until the engines build up to 95% thrust. The arms release on receipt of a launch commit signal at the 0 mark in the count. The vehicle is prevented from accelerating too rapidly by controlled release devices. The 6 million pound transporters move mobile launchers into the VAB and mobile launchers with assembled Apollo space vehicles to the launch pad. They are also used to transport the mobile service structure to and from the launch pad. 2 crawler transporters were constructed and are still used today to transport space shuttle vehicles. Maximum speed of the transporter is about 1 mile per hour loaded. The 3.5-mile trip to Pad A with Apollo 11 took about 6 hours. The transporter has a leveling system designed to keep the top of the space vehicle vertical within plus or minus 10 minutes of arc, about the dimensions of a basketball. The system also provides leveling operations required to negotiate the 5% ramp which leads to the launch pad and keeps the load level when it is raised and lowered on pedestals. The transporter moves on a roadway almost as broad as an 8-laned highway and is designed to accommodate a combined weight of about 18 million pounds. The roadway was built in 3 layers with an average depth of 7 feet. The base layer is 2.5 feet of hydraulic fill. The next layer consists of 3 feet of crushed rock. The top is covered with a cover of river rock, 8 inches deep.
This is Apollo Saturn Launch Control. We're at T-minus 2 hours, 55 seconds and counting. We're approaching the 2-hour mark in our countdown, and we appear to be proceeding satisfactorily at this time. The crew aboard the spacecraft, the 320-foot level. The hatch is closed, and we're beginning to purge the cabin to bring it to the proper atmosphere for launch, which is a combination of oxygen and nitrogen, 60% oxygen and 40% nitrogen atmosphere. Of course, the astronauts themselves are breathing pure oxygen through their spacesuits. Coming up shortly will be another key test in which both the launch crew for the launch vehicle crew and the spacecraft team combine together with the commander, Neil Armstrong, to make a thorough check of the emergency detection system. This is the system that will signal the astronauts in the cabin if anything goes wrong below them. We use the ground-based computer to accomplish this test. It's rather lengthy as these tests go using a computer. It will take some 30 minutes. Neil Armstrong will be doing most of the work in the spacecraft, responding as different cue lights signifying different difficulties are presented to him. The abort panel, of course, is across from the commander on the left-hand side, the left front of the spacecraft. Our countdown continuing, T-minus 1 hour, 59 minutes, 34 seconds, and counting. This is Kennedy Launch Control. This is Apollo Saturn Launch Control, T-minus 1 hour, 50 minutes, 55 seconds, and counting. We're proceeding with the countdown for the Apollo 11 mission at this time, and it's going satisfactorily. At this point, the spacecraft commander, Neil Armstrong, in the process of working the emergency detection system test. This is a check of the emergency detection system, working with the launch crew here in the firing room, and also the spacecraft team in control rooms back at the Manned Spacecraft Operations building here at the Kennedy Space Center. All going well with these tests at the present time. We're flowing hydrogen back into the third stage of the Saturn V launch vehicle after having difficulty with that leaking valve. It appears that we are bypassing the use of the valve directly in loading the hydrogen aboard, but we are getting the hydrogen back in to replenish the supply. All appears to be going well at this time. Weather is go. We're coming up on 1 hour and 50 minutes. This is Kennedy Launch Control. This is Apollo Saturn Launch Control. T-minus 1 hour, 40 minutes, 55 seconds, and counting. The countdown still proceeding very satisfactory at this time as we lead up toward our planned liftoff time of 9:32 a.m. Eastern Daylight. The spacecraft commander, Neil Armstrong, continuing this extensive series of checks of the emergency detection system, working with both the launch vehicle test crew and the spacecraft crew. This is a key test and a very thorough test to assure ourselves before we commit to liftoff that all the emergency detection techniques inside the launch vehicle are operating properly here on the ground, so if required in flight, the spacecraft commander and, of course, his two fellow astronauts could be signaled of a difficulty inside the rocket and could take proper abort action as required. Thus far, the three astronauts aboard the spacecraft have just been giving business-like responses back to the directions and checks, working with the spacecraft conductor, Skip Chauvin, as he runs down his procedures as the countdown continues. For T-minus 1 hour, 39 minutes, 46 seconds and counting. This is Launch Control.
Just like this.
This is Apollo Saturn Launch Control, T-minus 1 hour, 30 minutes, 55 seconds, and counting. All elements are go with the countdown at this time. The countdown aimed toward landing 2 astronauts on the moon. At this time, the spacecraft test conductor, Skip Chauvin, going through some checks with astronaut Mike Collins aboard the spacecraft. We're winding up this important emergency detection system test that Neil Armstrong has been participating in. Meanwhile, at the 320-foot level, the closeout crew now placing the boost protective cover over the hatch now that we have completed the cabin purge and have the proper environment inside the cabin. We have also performed leak checks to assure ourselves that the cabin atmosphere is valid. This boost protective cover is used during the early phases of the powered flight and is jettisoned with the escape tower shortly after second stage ignition. Here in the firing room, the launch vehicle test team still keeping a close eye on the status of the propellants aboard the Saturn V launch vehicle. We're back to 100% supply with the liquid hydrogen fuel in the third stage. This problem with the leaking valve is no problem at this time. We've actually bypassed the valve, but we are maintaining our hydrogen supply aboard the vehicle. All aspects go. The weather is very satisfactory for launch this morning. A thin cloud cover about 15,000 feet. Temperature at launch time expected to be about 85 degrees. T-minus 1 hour, 29 minutes, 30 seconds, and counting. This is Kennedy Launch Control. This is Apollo Saturn Launch Control. T-minus 1 hour, 20 minutes, 55 seconds, and counting. All still go with the countdown for Apollo 11 at this time. At this point in the countdown, Spacecraft Commander Neil Armstrong once again appears to be the busiest worker in the spacecraft as he's performing a series of alignment checks associated with the guidance system in the spacecraft. He's working these checks with the spacecraft test conductor as the spacecraft test conductor reads off the various procedures and Armstrong responds to them. The astronauts aboard the spacecraft also were informed by the spacecraft conductor a short while ago that the launch vehicle is go at this time. The hydrogen problem that we did encounter earlier has been solved. That's real good news, said Armstrong, and then he went back to work shortly thereafter. We're now coming up on the 1 hour, 20-minute mark in the countdown. This is Kennedy Launch Control. This is Apollo Saturn Launch Control. T-minus 1 hour, 11 minutes, 55 seconds, and counting. The countdown for Apollo 11 still going very satisfactorily at this time. In most cases, we're a matter of 5 or 10 minutes ahead of the countdown procedures. The crew in the White Room at the 320-foot level who have been aiding the astronauts up to this time are just in the process of finishing up their work. They've been advised by the spacecraft test conductor that they'll probably be able to move out in about 3 minutes or so. Once this is accomplished, once the closeout crew does depart, we'll be ready to move that swing arm back, swing arm 9. It will be moved 12 degrees away from the spacecraft hatch. This is about 5 feet away from the hatch. Once this is accomplished, we will arm the pyrotechnic systems in the spacecraft so in the event of a possible catastrophic condition below them with the launch vehicle, while still on the pad, the astronauts could fire that escape rocket and separate from the rocket in difficulty. The closeout crew about to depart at this time. That swing arm remains about 12 degrees away from the spacecraft hatch, as mentioned, 5 feet or so, until the 5-minute mark in the count when it's fully retracted to its fallback position. The obvious reason here is in the event we do have to get the astronauts out in a hurry, the swing arm is in a standby position and can be moved rapidly back to the hatch level so the astronauts could depart in the event of an emergency. We're coming up on T-minus 1 hour, 10 minutes, and 20 seconds. This is Kennedy Launch Control. This is Apollo Launch Control at 1 hour, 7 minutes, 25 seconds, and counting. Countdown still proceeding satisfactorily. For those people who would like to synchronize their watches in relation to the count, will synchronize on 26 minutes past the hour, which is now about 65 seconds away. We'll count down the last 5 seconds to 26 minutes past the hour. We're now 1 minute away from 26 minutes past the hour. In the meantime, we do have information from the civil defense agencies in the area. The estimate is more than 1 million persons are in the immediate area in Brevard County to watch the launch. Now 40 seconds away from 26 minutes past the hour. Civil Defense Agency reports further that there is extensive heavy traffic, a number of traffic jams, particularly in the area of Titusville, near US 1 and Route 50. Countdown still progressing satisfactorily, 15 seconds away from 26 minutes. 5, 4, 3, 2, 1, mark. 8:26 a.m. Eastern Daylight Time. We're now 1 hour, 5 minutes, 55 seconds and counting as it was announced at that point. This is Kennedy Launch Control. This is Apollo Saturn Launch Control, T-minus 61 minutes and counting. T-minus 61 minutes on the Apollo 11 countdown, and all elements are go at this time. Astronaut Neil Armstrong has just completed a series of checks on that big service propulsion system engine that sits below him in the stack. We want to assure ourselves before liftoff that that engine can respond to commands from inside the spacecraft. As Neil Armstrong moved his rotational hand controller, we assured ourselves that the engine did respond by swiveling or gimbaling. This, of course, is important for maneuvers in space. The countdown is still proceeding very satisfactorily, other than 2 minor problems. Since we picked up the count at 11 p.m. Eastern Daylight Time last night, all has gone well. As we approach the 1 hour mark now in the count, a series of radio frequency and telemetry checks will be in progress with the launch vehicle. We'll also check out the tracking beacons in the instrument unit that travels as a guidance system for the Saturn V during the powered phase of flight. Now 59 minutes, 48 seconds and counting. This is Kennedy Launch Control.